The way you push this engine is actually by sending the steam in. You actually have two valves here to control the inlet and outlet of the steam. We open the valve, we send the steam in. Once the steam goes into that small chamber, it's going to push this piston down and it's going to start to rotate. And once it rotates to here, we open another valve to let the steam go out so that you can continue this circular motion. By controlling the inlet and outlet of the gas, you can push the wheel to move. So this is actually one of the most important inventions back to that time. People actually spend a lot of time trying to figure out what would be the maximum efficiency we can actually achieve. They want to actually know how much of the heat can be converted into work. So that's actually the key problems back to that time. Carnot is an engineer and he's actually the person who solved this problem. Okay, so of course we cannot do all these things using an open system, right? So all the things we learned so far is actually we use closed system. Carnot think about if today I have a gas inside, if I can actually change the volume of the gas, I can actually start to push the wheel to turn. And then once it turns to this point, if I can actually make the volume of the gas smaller, then this thing can actually continue, right? If today, here is actually my gas. If I put a good conductor at the very top, then I use that tap to connect to two different heat reservoirs. Heat reservoir is a bulk pieces that can store infinity of the heat. When you put this engine to touch it, then the heat can go from your heat reservoirs to your engine. So once that happens, because the gas now got a lot of heat, then it's going to do the expansion. So the volume of the gas is going to become larger so that you can start to push your engine and make it move. Once you make the half turns, I actually put it into another reservoir. So this is actually a low temperature reservoir. This is a high temperature reservoir. Once I do that, then because right now the heat can go from your gas to the heat reservoirs. So the temperature of your gas is going to decrease. Therefore, the volume of the gas is going to shrink. Therefore, you can actually make the second half turns. Basically, what it does is actually I just move my engine, touch the heat reservoir, so that the gas is going to expand the volume to push the engine. Once it makes the half turn, I move it to get in contact with the low temperature reservoir. So the volume of the gas shrink, so you can actually make the second half turn for your engine. By repeating this process, basically contacting different reservoirs, then you can still create this cycling motions of the engine. So once you have that in mind, your system is this part, okay? That is your system. Inside, you only have your gas. All the things we discussed is actually a property of that small pieces of the gas. All the property we talk about is this guy. To fully describe these processes, we actually need 4 steps. I want to change this one as A, B, C, and D. And then the next thing I want to do is to plot out how these 4 steps is going to look like on a PV plot. Because right now I really care about how the pressure, how the volume, and how the temperature of the gas in my system going to change. Here, because we have 2 reservoirs, right? One is called the T1. The other one is actually, let's call it T3. Okay, we have 2 different temperatures. And assume we have ideal gas. If we apply out the isosome at 2 different temperatures, we should see something like this. So these are 2 isosomes. On the top is actually high temperature. Let's call it T1. Bottom is actually T3. So let's say we want to start from this initial point. I want to actually get in contact with my high temperature reservoir. We are going to do a reversible isothermal expansion. Okay, so I'm going to get in contact with high temperature reservoir. And then I let the gas inside my system going to undergo a reversible isothermal expansion. So once that happens, we know the volume is going to increase. Concurrently, you will see a decrease of the pressure. So that's actually your A. So this will be your point 2. When you move it from here to here, so you are going to still undergo a reversible adiabatic expansion. Once you do that, the temperature is going to decrease. Because right now you don't have any heat source from your environment, but you still want to do the expansion. Therefore, your temperature is going to decrease. Once you go to this part, so this will be your step B. And then you get in contact with your low temperature reservoir. So under this case, you go back to the isothermal things, but right now because the temperature is low, the volume is going to get smaller. So you actually undergo a isothermal compression. This is actually your point number 3, and that's your point number 4. And then this will be your step C. Eventually, you want to go back to your original state. So once you contact for a while, you want to move your system back to center so that it will eventually undergo a reversible adiabatic compression. So you can just get back to your first point. Okay, so this will be your step D. All these 4 steps are the steps we already know how to calculate, how the heat, the work, and the PMV. Okay, that's actually things we discussed in the previous lectures. I want to put a few more thoughts onto this part. When we say the first step is actually reversible isothermal expansion, we go from point number 1 to point number 2. So if we say the pressure, volume, temperature of your point 1 is P1, V1, T1, and it's going to go to point number 2, which should have P2, V2, T2. But because you are actually doing the isothermal expansion in this case, so that means actually the temperature is going to remain the same. So you know your T2 is going to equals to your T1. And then you undergo a reversible adiabatic expansion. So we know you start from the P2, V2, T1. It's going to expand into P3, V3. Now you actually go to T3. And then it's actually you undergo a reversible isothermal compression. That means actually you're going to go from P3, V3, T3. You're going to go to P4, V4, T, because it's actually isothermal, right? So T4 is actually equals to your T3. So at the very last part is actually you go from P4, V4, T3, and become P1, V1, T1. Okay, so that's actually how the PVT is going to evolve after you finish a full cycle.